Okay, I think it's 10 to 10, so we can start to be on time. Welcome everyone to the morning session of the third day of the workshop. Our first speaker is Yonina Eldar. She is a professor of electrical engineering at the Department of Mathematics and Computer Science at the Weizmann Institute of Science. And she has been since 2019. Before that, she was at Sept, where she has been since 2002, first as a lecturer, then as an assistant professor, and then as a full professor. She got a PhD from MIT in 2002, where she's still the full professor. Today she will talk about model-based deep learning applications to imaging and communication. So please, the floor is yours.
Okay, great. Thank you very much. And I envy all of you that could be there in person. So it would be much more fun to be there in a hall with everyone than to be talking in front of my own screen. But hopefully I could get the ideas across this way as well. And, you know, I think we all hope that we'll all be able to meet again soon in person. So with that, let me thank the organizers for inviting me to the workshop and more generally, you know, to the entire session over these few months. So what I want to talk about today is how we can try and combine benefits of model-based ideas that we're very familiar with in signal processing and communications, together with, you know, deep learning, learning from data, etc., which of course everyone here knows why it's important and we don't need to motivate it. So that's really what we're going to try and talk about today. We'll see some applications to some problems in imaging and communications, and mainly, you know, this is definitely all work in progress. So if anyone sees anything that looks interesting to them, I'd be really happy to discuss more offline. So we all know today, of course, that, you know, deep learning has revolutionized many fields, and it's been used heavily in almost any application we can think about, where it's particularly been successful in applications that don't really have good models, like computer vision or speech processing. So these are problems that traditionally were quite difficult to tackle using kind of standard conventional optimization methods. And that's part of the reason why deep learning is so successful, particularly in these areas. So we know that we could do, you know, really cool stuff with deep learning. We could spawn fake faces, which are, you know, look very much like real faces. We could get a detection rate that, you know, is better than human performance on many different databases. But there's also many difficulties with deep learning, especially when we're looking at applications that we've been looking at, like radar, communications, medical imaging. So these are all areas where traditionally we're used to having interpretable methods, we're used to having models that we rely on in developing our different approaches. So part of the difficulties are that to get the good results, we really have to have, you know, large training sets. It's not really clear how to interpret the methods that we get. Sometimes there's a feeling that, you know, you put everything you have into the problem, and if it doesn't work, you just kind of stir a little bit more, and then all of a sudden it does work. So it's not always clear what's making these methods work. It can be really demanding to train the methods. Robustness and generalization are not always clear, and very often the methods don't generalize well. The complexity could be huge. So if we look at GPT-3, for example, you know, the leading method in human text translation, it uses 175 billion parameters. So, you know, that's good for areas where we maybe don't have alternatives. But if we're looking again at problems that we're used to looking at in signal and image processing, 175 billion parameters is, you know, a huge amount. So the question is whether we can try and overcome some of these challenges. Now, if we take a look at signal processing, or what we traditionally did in signal processing before the era of deep learning, we know that our methods are based on modeling. Because they're based on modeling, it's very easy to incorporate different things we know about the problem, domain knowledge, structure. We could get inference from a relatively small amount of data. And we also have very nice analytical techniques to assess the quality of the output, which of course gives us robustness, generalization properties, etc. So these are some of the advantages of signal processing or model-based learning. But of course, they all rely on the fact that we have very accurate model knowledge. Okay, if we don't have a model, then we can't use these methods. And even if we do have a model, the model may be very complicated, so it may not be so easy to apply these more analytical methods. And of course, the inference could be relatively slow. So the question is, you know, could we somehow merge the benefits of these two techniques. And that's really what we want to talk about today. So how we can use ideas from model-based learning and incorporate them into data-driven systems. So to see how we could do that, I'm going to give, a pictorial view, or really a bird's eye view on model-based learning versus deep learning, and then we'll see kind of how we can merge them, and we'll go into more details in the rest of the talk. So on a really, really high level, we could think of signal processing methods as methods that get an input, some measurement, we're going to call it Y. So it could be, for example, a noisy image. And what we want, our desired output, is some vector X, so maybe that's the clean image. And then we have some predefined model that relates our noisy measurement Y to our desired output X. So we assume, for example, that Y is approximately equal to G of X, where G is some known function. And then in order to find our output X, we're going to optimize some metric function, which is denoted here by F. So it could be, for example, some norm, although it doesn't have to be a norm. So we're going to, let's say, minimize, the squared error norm between Y and G of X, and that will give us the desired output X. Now, in practice, this will typically not have a closed form solution. So what will happen in practice is that we'll derive some iterative algorithm using, let's say, gradient descent or proximal gradient descent or ADMM or your other favorite iterative technique. And when we apply this iterative technique, what we'll typically get is something like this. So we'll have some pre-processing. We'll then have iterations, right? Because we're going to repeat this many times. And the iterations themselves, we could usually break down into two blocks. A block that is something generic that doesn't depend on the particular model, and then a block that's model dependent and could contain parameters that we may not know if we don't know the model in advance. And then we'll typically have some post-processing and obtain our output X. Okay, so this is kind of a very pictorial view and how signal processing would work in these types of problems. Now, on the other hand, if we look at deep learning, the picture, of course, is going to be very, very different. So we're going to have some fixed architecture that we fix in advance. It's not necessarily related to our specific optimization problem. We then have pairs of many inputs and many outputs that are paired together. And this is our training data. And we're going to use that in order to learn the weights in this architecture that we pre-specify. And then when our new input Y comes in, we're going to put it through this trained network and hope that, miraculously, we're going to get a good output X. Okay, so we could think of these as the two approaches that we want to try and merge. Obviously, they're very different. And the way we're going to merge them is by two main techniques that I'm going to outline next. So the first is by using what's known as unfolding or unrolling, where basically we use the optimization algorithm to get the architecture of our network, but then we use the training data to learn the specific unknown parameters. So that's what we're going to do in unfolding. The second approach, rather than starting from the original optimization problem, is actually going to start from the algorithm itself. So the second approach is good for methods where we have a very good algorithm. It could be a heuristic algorithm, but it's a very good algorithm for the problem. But the algorithm itself depends on unknown parameters. So in that case, we're going to keep the flow of the algorithm, but use a network, which is typically going to actually be quite shallow. We're going to use a network only in the blocks that depend on the unknown model. Okay, so these are the two approaches that we're going to use, and I'm going to outline next how these two approaches look in a little bit more detail. So the first idea of unfolding or unrolling goes back to the really beautiful paper of Gregor and LeCun from over a decade ago. So, it's not a new idea, but it has been largely overlooked until recent years, where people have gone back and revisited this approach and generalized it in many ways. So the idea of unfolding, as I said, is to start from our iterative algorithm. So this is the same iterative algorithm, we showed kind of pictorially before. And now what we're going to do is we're going to write down a finite number of steps of the algorithm, typically a small number. So in most of the applications we looked at, we didn't use more than 10. So usually, T here will be equal to roughly 10. So we'll write down the specific steps of our iterative algorithm. And now what we have end to end is just 10 steps of our iterative method. Okay, so there's no learning yet. We're just implementing the iterative technique. But then in the last step, what we're going to do is in each of these iterative steps, there's going to be parameters that depend on our model. And we're now going to free them. Okay, that's the terminology, and basically learn them from training data. So the architecture is going to come from our optimization step, but the specific parameters are going to be learned from training data, and we could learn them differently in each individual layer. So this is what's known as unfolding. For those of you interested, we have a recent review together with Vishal Manga and his former student, Yulong Lee, on algorithm unrolling in Signal Processing Magazine. So you could take a closer look. But the nice thing about unrolling is that it allows us to incorporate, our optimization techniques. It gives us interpretable methods. We have control over the method, and it tends to lead to very good performance from small amounts of training data. So let's just take a closer look on how this works for a problem that everybody's familiar with, sparse recovery. And this is the original problem that Gregor and LeCun looked at. So suppose we have a linear measurement model where our measurement is y. It's observed through some known matrix A multiplied by an unknown sparse vector x with additive noise. And we want to find, our sparse vector x that generated the data. So, one of the probably most popular techniques is using the L1 regularized least squares problem. And a popular method for solving this problem is using the ISTA algorithm, iterative shrinkage at thresholding, which basically takes a gradient step of this consistency term and then performs a proximal step, which is a soft thresholding to enforce the L1 term. So if we look at one iteration of the ISTA algorithm, we're going to get the gradient. So these two terms are coming from the gradient, and they of course depend on knowing this transfer matrix A. Mu here is a step size. And then we have the proximity operator or the soft thresholding that's going to depend on this parameter lambda. Okay, so this is what one step in the algorithm looks like. Now to unfold it, and this leads to what's known as LISTA, learned ISTA, going back to the work from Gregor and LeCun, we take this basic step, we write it down k times, okay? So this is the unfolded method. And now we're going to free the parameters. So instead of assuming, let's say that lambda and mu are fixed, we're going to learn them in each layer. And we could even go further. If we don't know the matrix A, we could learn the matrix A, or we could just assume that these are two independent linear blocks and learn these blocks in each layer. Okay, so there's different levels of how we want to free the parameters, how many parameters we want to free, but they're all inspired by this basic iterative step. Okay, so when we do that, we end up with a deep learning method where we learn these parameters from training data in advance, but the architecture, each layer is based on the optimization problem that we started with and the optimization method that we decided to use. So this ends up giving us interpretable methods. The learning is very fast. We don't need many layers. We don't need a lot of data. And of course, at the end, the method is going to have a low complexity and low memory footprint because there's not a lot of layers and not a lot of parameters. So this is the general method of unfolding. We're going to see various ways of implementing it throughout the talk. The second method is what we call hybrid methods. And these are good for problems where we don't necessarily go back to the original optimization algorithm, but we have some basic method that turns out to be very good in practice. So for example, the Viterbi algorithm in communication, which is implementing dynamic programming. So we know that dynamic programming is very useful, and therefore we want to keep it. We don't want to change that. We don't want to replace that by a deep network, but it may have parameters in it that depend on the unknown model. And therefore what we do is we keep the generic method, but every time there's some block that depends on the model, we just replace that block by a network. And typically this network is going to be quite shallow because we're only replacing a specific block. We're not replacing end-to-end learning. So we end up with an algorithm that looks very similar to the original algorithm we started off with, but we're learning the parts in the algorithm that we don't know in advance. Okay, so we'll see later on some applications of these ideas to problems in communication. And again, those of you interested, we have a recent review on this technique, which you could go ahead and take a closer look at. Okay, so hopefully that gives you, an overview of the types of methods we're going to be using for combining model-based learning, for combining models with deep learning. And what I want to do next in the rest of the time that we have is take a look at different applications. So let's start with applications to imaging and ultrasound, where we're going to start with a very, very basic application, just, standard image deblurring. There's, of course, been, hundreds, if not thousands of works on image deblurring. And this is work that, again, was done with the group of Vishal Manga. So what we wanted to see is if we could get, comparable results to sophisticated deep networks using this very simple idea of unfolding. And what we're going to see is that we could actually surpass existing networks, even though we're using a very simple technique. So for our unfolding method, we have to start with the optimization problem. And what we're going to do is we're going to look at a total variation criteria in the gradient domain, and then solve it by using a variable splitting approach or an ADMM type approach. So to be more specific, what we're going to do is we're considering an image deblurring problem. So we don't know the original image and we don't know the kernel. So we're going to set up an optimization problem where K here is the unknown kernel. So of course we want to minimize over K. And we're going to assume that K has a norm bound. Okay, so we're constraining the norm of K to put some normalization on the unknown blur. And then in terms of finding our original image, instead of searching directly for the original image, we're going to search for features of the image. So these are these features GI. And we want these GIs, these features, to match filtered versions of our measurements Y. Okay, so for example, we could look for features that match the gradient. Okay, so in the optimization problem, we're searching for the unknown kernel K, and we're searching for the unknown features. Once we have the features, we could go ahead and reconstruct our original image X. Okay, so the difficulty, of course, is in finding the kernel and finding the features. And here, Fi is assumed to be fixed. So we're looking for the features that match certain filtered versions of Y. But when we unfold the algorithm, we're not going to assume that these Fi's are known, but rather we're going to learn them together with learning the GIs and the underlying X. Okay, so we look at this problem, we set up a variable splitting or ADMM approach to this problem. So this leads to the method that you see over here. And again, you could go ahead and look at the paper for all the details, but this is basically just ADMM on this optimization problem. And then in the learning step, we also learn these feature maps Fi. Okay, so this gives us a very simple method. It has 10 layers. It doesn't have many free parameters. And here you see a comparison of this method, which we call doubled. So that stands for deep unrolling for blind deblurring. And we compare it to the leading methods that we found in the literature that are based on, much more complicated deep networks. And we see that we could get better performance, even though we train on a very small data set. And the code for this method is freely available from the first author's website. So you could go ahead and play around with it and see how it works for yourself. But it really follows the optimization technique. So it's quite simple to implement in practice. Okay, now, of course, when we implemented that method, we assumed that we had a proximal gradient approach. So we assumed that we had some regularizer. And if we go back over here, our regularizer was an L1 regularizer on these feature maps. But in general, we may also want to learn the regularizer. So we may not know the best regularizer in advance. And if we go back to images, this could be the case when we have more complicated imaging problems like image in painting, okay, when we have whole areas that we have to fill in. So what we did is we took the same approach of deep unfolding, but now we also want to learn the regularizer, and we do that by using invertible flows. So there's been a lot of work in recent years in learning flows or GANs or PDFs in advance from a given database. So there's been, a lot of really nice work that basically learns, let's say, a GAN, and then applies that to denoising or deblurring. What we want to do here is merge those two steps. So we want to learn a PDF, but we want the learning to be in an unfolded version so that we continuously update the parameters of the PDF as we go through the network. So to do that, we use the concept of normalizing flows or invertible flows because they're very easy to handle and they're very easy to apply gradients to. And what we got a first learning in advance, but then we propagated the PDF through the network so that we learned it together with the unfolding steps. And this, of course, leads to much better performance. So here we're comparing our approach. So this is the proposed approach over here with, other state-of-the-art deep learning methods that have been applied to this problem. And this is work that was done together with a group of Ruud van Sloan, Professor Ruud van Sloan from Eindhoven University. So we're integrating these invertible flows into the unfolded networks. And as you can see, it gives very, very good results, again, using a rather simple network, which is simpler than the alternative approaches and gives better performance. Now, we can use this for many other optimization problems as well. So first, we looked at deblurring. We've used this, for example, for separation. So separating in this particular case, going to ultrasound, we wanted in this video, let me show it again, we basically want to separate background tissue, as you see over here, from blood flow. And this is a really important problem in ultrasound because you want to be able to view the blood flow, but when you have the strong tissue in the background, you can't see it. So what we did here is we modeled the problem as a low rank plus sparse problem, where the fixed tissue is modeled as low rank and the blood flowing is modeled as something that is sparse. But the low rank and sparse wasn't really strong enough to perform the separation. And that's just because, this is just an approximate model. It's not really exact. So we use that as a basis for unfolding, and this improved the results considerably. So I'm going to show what we did next, but those of you interested, we have a review, again, together with the Weizmann Sloan's group on deep learning, specifically in ultrasound imaging, and there we go into much more detail on these various techniques. So what we did here is we set up an optimization problem where we have data and we're looking to decompose it as a low rank plus sparse, where we're using a robust PCA version. So we have a low rank constraint on the low rank part and a sparsity constraint on the second part. So this is, a standard robust PCA problem. We could try to solve it using, again, proximal gradient, and we'll get these types of iterations. I'm not going to go into great detail here. So this is one iteration of robust PCA. But now what we're going to do is we're going to unfold it. So we're going to write this down several times, free the parameters, and learn them from data. And this leads to a learned version of robust PCA, which gives us very good separation between the tissue component and the blood flow components in practice. So we see that we could use this for various different types of problems. Just one more application in ultrasound. We've used this also for adaptive beamforming. So beamforming, it's used in ultrasound, it's used in radar and many other array processing problems, where basically we have multiple antennas and we want to align the signals in the different antennas and focus them to a different direction. So there's been many adaptive beamforming methods that have been proposed in the literature, but here again, we use this model-based approach to learn the adaptive weights from data, and this leads to much clearer images, as you can see over here. And this again is work that was done together with a group of Weizmann from Weizmann. We've been using this more recently for COVID-19 detection. So when COVID started, we opened a task force in our lab with several different hospitals in Israel, where we looked at how we can use these ideas of model-based learning for both detection from X-ray and detection from ultrasound. And we've been able to get really good performance by using these model-based approaches together with standard deep networks. So those of you interested could go ahead and take a look at our papers. We have one paper on X-ray and another paper that we've been working on with the group of Professor Libertario Demi from Italy on using similar ideas in the context of ultrasound. Okay, so with that, I'm wrapping up what we wanted to say about imaging. I want to show next how we can use these ideas for super resolution, and we'll look quickly at examples in both microscopy and ultrasound. So super resolution microscopy is a very exciting, important topic. The issue is that when we use an optical microscope, we're limited by Abba's diffraction limit to half the wavelength that is used for illumination. So in the optical regime, we can see, for example, bacteria and cells, but we can't see proteins and small molecules, which is what we're interested in from a biological point of view. Now, in 2014, the Nobel Prize in Chemistry went to this really clever idea of optical fluorescence microscopy. And the idea was to introduce fluorophores into the object we're trying to image and to control them so that instead of taking one image, we take thousands of images or thousands of exposures, where in each exposure, only a small number of fluorophores are actually fluorescing. So instead of having, this is a diffraction limited image. This is the image when everything is blinking, but of course it's hard to super resolve. So instead what we do is we take thousands of images where in each image you get only a small number of green dots. And then if you assume that each green dot is just coming from a single fluorophore, then you could just stick a Gaussian every time you see a green dot, sum over all the exposures, and you'll get one super resolved image. So this was the idea. It's super clever, and that's why, of course, it was awarded the Nobel Prize. But the difficulty with this concept is that it gives very good spatial resolution at the expense of temporal resolution. So now to get one image, we're taking thousands of exposures, and that requires a lot of time. So this precludes doing this in real time. So what we wanted to do is to see if we could get both high spatial resolution, and high time resolution. And what we did is first we did this without learning. So we did this by using a model-based approach, which we call SPARCOM, sparsity-based super resolution correlation microscopy, where basically we're exploiting sparsity in the correlation domain. And more specifically, we're using a sparsity prior on the fluorophores, but also using the fact that they fluoresce in an independent fashion. So if we look at the covariance matrix of the fluorophores, it's going to be diagonal, okay, because the fluorophores fluoresce in an independent fashion, and the diagonal itself is going to be sparse because the fluorophores are sparsely located. So basically, we solve a sparsity problem in the correlation domain, and this gives very good performance. So here we're comparing the ground truth to STORM, the method behind the Nobel Prize that uses 12,000 exposures, and we're comparing it with SPARCOM, our technique, which uses only 300 images, so we get very good time resolution and very good spatial resolution. Here at the bottom, we see that with 50 images, we could get better resolution than you would get with STORM with 500 frames. Okay, so this is work that we did several years ago together with a group of Moti Segev from the Technion, and we were able to get super resolution. The drawback, however, is that in order to do this, we require knowledge of the PSF of the system and other system parameters, which we don't always know in advance. So the next natural step is to unfold this idea. So we get in learned SPARCOM, an unfolded version of SPARCOM. And the nice thing about this is that it's very, very quick. It works really well. We did training only on a single image. We get better resolution even than we got from SPARCOM. And the most important thing is that we don't have to know anything about the system. So everything is learned from the given training data. And as I said, we're only training from a single image. So here you see that we could get really, really impressive resolution, and this could be done very quickly in time. So together with a group of Gilad from the Weizmann Institute, we've been applying this technique to live cell imaging. And in particular, Gilad is interested in the behavior of T-cell receptors. And we're really excited. We're getting preliminary results of being able to analyze the T-cell behavior in real time at super resolution using this technique. So that's what we could do in microscopy. The next thing we wanted to do is to see if we could use this to super resolve ultrasound, because ultrasound is also diffraction limited. Now, of course, we can't inject fluorophores into the body, or we don't want to inject fluorophores into the body. But what we could do instead is use this soda view bottle. So these are basically micro bubbles that are FDA approved, and we can inject them into the bloodstream. And they're used today to try and improve contrast. So what we did is use these same bubbles that are already approved, but we're going to use them not for contrast, but actually for super resolution. So it's very similar to the microscopy, where the bubbles are flowing through the blood, just like the fluorophores are blinking in the microscopy problem. So this is a clinical study that we did together with Dr. Ahuva Grubstein from Bellington Hospital. This is Ahuva and her team. Sorry, Ahuva and her team. And these are the scans that we actually did in the hospital. And what we did is we scanned patients with breast cancer, where today it's very hard from ultrasound to see if they have a tumor, if it's benign or malignant. And using these super resolution techniques, we were able to get sufficient resolution to be able to determine that from ultrasound alone. So what I'm going to show you now is just 2 images. Those of you interested, we published a clinical study so you can see more details. These are 2 images of 2 different patients. And if you look at the top image, in both of them, you could see a mass. Okay, so the mass is clearly visible, but both of them just look like a black hole. So it's very hard to determine if the mass is malignant or not. This is the state-of-the-art method used based on contrast, but again, all it does, it makes everything very, very bright. It doesn't give you better resolution. And here you see our deep unfolded method, where clearly you could see a difference between this mass and this mass. So the vasculature is very different. Here it's only at the edges, and here it's throughout the entire mass. And from this, the doctors were able to determine immediately that this is a non-malignant, a benign tumor, and this is unfortunately a malignant tumor. And here we verified it with other scans that we had of these patients, so we can tell that these methods are very effective, and they allow you to determine the behavior of the mass from ultrasound alone. So that we were very excited about. One last topic I want to mention, and this is work that was done together with Professor Miguel Rodriguez, was that we can use these unfolding methods to get robust techniques as well. So we could even go back to the original list of problem, but assume now that we have a model mismatch, which is different from sample to sample. So what we could do here is use robust optimization and then unfold a robust optimization technique. And this leads to what we call REST, robust learned shrinkage thresholding. So we start from a robust optimization method, we unfold it, and this will give us a robust version of Lista that is now going to be robust when there is random errors that are different in each realization. Okay, so that's kind of, I spoke a lot about unfolding. That's really the main technique that we've been using for combining model-based with learning. And let me just take, I think I have a few minutes left, so let me just very, very quickly talk about the second technique, which we've used primarily in the context of communication. So in the second method, as I said, what we do is we start with the method itself. And every time we have a computation that's based on a model, we replace it by a simple network. Okay, so we've used this for many problems, for Viterbi, for Kalman tracking, and many, many more. So let me just briefly show the main idea. So the first approach that I want to show this on is the Viterbi algorithm, which is, the most popular method for symbol detection and communication, and all cell phone todays implement the Viterbi algorithm. So basically, it's a maximum likelihood sequence detector based on dynamic programming, assuming that we're using a finite memory channel. And what the method actually does, without going into too much detail, is that at each stage, it computes the likelihood of a given set of symbols, and then it performs dynamic programming over this trellis graph, which basically starts from, let's assume that the first symbol was a 0, then let's assume that, what the options of the next symbol could be, etc. And it accumulates the likelihood as it goes through this graph. So it's a dynamic programming approach to go through this graph efficiently. And what's interesting when you look at this Viterbi algorithm is that the dynamic programming itself does not assume any knowledge at all. You can always implement it. The part that assumes knowledge of the channel is this likelihood calculation. Now, there's been many, many works in the literature that basically take, this basic symbol detection problem and replace it by an end-to-end deep network. But those methods, require a lot of training data, and they're very sensitive to the channel model. So if you train in a one-channel model, and then the SNR even changes a little bit, the methods no longer work. What we said instead is there's no reason to replace this. Dynamic programming is actually very good and very efficient. The only thing we actually need to replace is the likelihood computation. So instead of doing end-to-end learning, we now keep the dynamic programming and only learn the likelihood. And this leads to what we call the Viterbi net. This was work that was done together with Professor Andrea Goldsmith groups. And this leads to very effective behavior. So we could get training from a very small training set. In fact, it could fit in the current overhead of the symbols that are sent. So basically, we're not sending any additional training data. The method is very effective. What's nice is that when we know the channel, we get the optimal Viterbi performance. And when we don't know the channel, as you see here in the graphs, we get almost the same performance. And it's very robust to changes in SNR, small changes in the channel, etc. So it works very efficiently in practice. We can now do the same thing for many, many other problems in communication. So for example, we've looked at this for factor graph methods. So in factor graph methods, you have an underlying distribution that you factor, and then you do message passing over the graph. So here again, instead of replacing everything by an end-to-end learning when we don't know the underlying distribution, what we suggest is to keep the message passing and only learn the particular factors. So we learn the factors, but we keep the message passing. Just like in ViterbiNet, we keep the dynamic programming and only learn the likelihood. And this, again, is very effective in practice. The final thing I want to point out is that we can use this also for greedy methods. So we've used this, for example, for successive interference cancellation, which is very popular, for example, in MIMO communication when we have interferers on the channel. And here again, we keep the flow of successive interference cancellation, but when we have to compute the likelihood or the probability of the strongest user, we do that by using a small classification network. So to sum up, and hopefully I'm wrapping up just on time, we've talked a little bit on how we could bridge maximum likelihood or machine learning, machine learning, the ML is always confusing, machine learning methods with signal processing methods by trying to basically get the best of both worlds. We've shown some methods, there's of course many other approaches that one can take. And I think one of the exciting open problems is trying to prove the good behavior that we see, and we have some first results along those lines, but that's definitely something that we're very interested in. So if anybody here could be interested in that, I'd be very, very happy to discuss further. So those of you interested, we have a recent review that goes into more details on all of these different techniques. And of course, none of this would have been possible without my amazing team of students. So I'd like to thank my students and of course, all my wonderful collaborators who have been working with me on these projects. And thank you very much for your attention. I'm definitely happy to take questions, and also very happy if anybody finds this interesting, very happy to discuss offline as well. So with that, maybe I'll open up for questions.
Yonina, you were perfectly on time, so we have 5 minutes now for questions. You can either write in the chat or be monitoring that, or just unmute yourself and ask directly. Are there questions from the audience to start with? Yes, Joy.
Hi, thanks for the talk. It was really interesting. I was wondering, you were talking about unrolled or unfolded algorithms which could be used to get this lista, for example, or make it. And I was wondering, instead of having a model that has some predefined size and length or a number of layers, would it be possible to change the architecture so that it would be more of a single loop, perhaps, that could be kind of given time to think as long as you can afford, but so it wouldn't be so big, basically?
Yeah, that's a really, really good question. So some things that we could do to make it a little bit more adaptive and not so fixed is that, like, instead of fixing the size, if we use, let's say, a local kernel, like a convolutional kernel, for example, then that can work for any size, right? Because we're not dependent on the size of the vector, and the, let's say, the linear matrices are not fixed in dimension, but rather, you know, they could work on any dimension because they're local. So that's one thing we do to overcome the fact that the input has to be fixed in dimension. In terms of adapting the layer size, that's a really good point. We've been looking at some methods to do that. I'd be super happy to discuss that more offline, because I don't think there's a really good, we've done some heuristic ideas. I'm not aware, and I should be careful because, you know, there's so much literature, there might be something that I'm not aware of, but I'm not aware of a very principled method to fix the size, the number of layers. And I think that's a really important question. So we've used some heuristic techniques, but not anything that's, you know, very well-grounded. So I definitely be happy to talk more about that.
Thank you.
Other questions from the audience?
Thank you very much, Yonina, for your talk. There is so much work. I'm very impressive. Could you please talk a little bit about what's the level of robustness of the different model? So when you say that you replace the complicated models with a shallow neural network, what's the level of robustness of that? So if the model changes just a little bit, would that break everything, or?
Yeah, good. That's another really, really good question. So yeah, so that's like kind of in the second technique. So in the second technique, the issue is that because we're not doing end-to-end training, the network comes into the method in a very particular point. So let's look at ViturbiNet, for example. So we're only using the network to learn the likelihood, right? Like not everything end to end. So learning the likelihood is a relatively easy task. Like, for example, you could think of a classification network, right? That just has to classify, you know, the possible bits and give them like a soft output, give the probability for the possible bits. So that you could typically do with something like 2 or 3 layers, just because it's a simpler task than having to learn end to end. Okay, so just we've observed empirically that you don't need many layers for that. In terms of robustness, again, because the tasks are rather simple, the networks just empirically tend to be very robust. We've also used the meta-learning approach. So when the changes in the channel are dramatic, like not just small changes in SNR, but let's say, you know, really larger changes, and you can see we go into this a little bit in the paper if you're interested. So we use like a meta-learning approach to kind of adapt that network to larger changes in the channel. But again, the beauty is that because it's something very specific, like calculating the likelihood and not an end-to-end problem, it's much easier to use these different techniques. So we're still lacking a fundamental theory, right? Like it would be nice to really prove this theoretically, and that is still hard to do, like many things in learning. So that's definitely something that we'd like to do. But empirically, because we're learning very, very simple tasks within this bigger context, we've seen that the methods appear to be very robust, and it's relatively easy to adapt them using, for example, techniques like meta-learning.
Any other question from the audience here? still don't see anything from the chat, then I guess we can thank you, Nina, again. And I think since Martin.
No.
Okay, sorry. So and waving. So we can thank you, Nina, again for the very wonderful talk.
Oh, thank you. And I envy all you guys for sitting there together.
It's actually now a morning tea break for the in-person audience. And I don't know if we're gonna continue the discussion. If anyone wants to talk more, I think we can also go further.
So also feel free to reach out. You can send me an email, and I'm happy to talk offline as well.
We reconvene in half an hour otherwise. So
All right. Thank you. Enjoy, everybody.
Yeah.
I would say it's up to perfect time. Okay, welcome back everyone to the second part of this morning section. Our next speaker is Matthias Eldar from the Department of Mathematical Sciences at the University of Bath. There he is a Leverhulme Early Career Fellow. Matthias got his PhD in 2015 from UCL. And then after postdoc first at UCL and then in Cambridge, he moved to the University of Bath, where he's also Prize Fellow at the Institute for Mathematical Innovation and co-director of the Center for Mathematics and Algorithms for Data. So today, Matthias will talk about the equivariant neural networks for inverse problem solving.
Thank you so much, Tatiana, for the very kind introduction and for the openness for the invitation. It's such a great pleasure to be back in person. So this is my first in-person talk since 1.5 years or so. So it kind of like feels weird, but also like it's a very positive weirdness that one is experiencing here. So kind of like the talk in a nutshell. So yes, indeed, I will talk about equivariant neural networks for inverse problems. But kind of like what this is all about is about to bring mathematical guarantees into like if you want to solve inverse problems via deep learning. And this is this joint work with like a number of people. To highlight maybe like one person here, that's Ferdi Sherry, a joint PhD student of mine, and Carola, who just submitted his thesis, who did the majority of the work here. All right, the outline of my talk goes as follows. So first of all, I would like to give some small introduction into inverse problems and how this potentially connects to machine learning. Then we talk about equivariance, and then finally, I would like to conclude the talk with some numerical results. And although I now wrote this as 3 parts, actually, like the part 2 is by far the biggest. So I could have equally split up this part in like 3 parts, and then we would have like 5 equal parts. All right, and like in case you want to know more about what I'm talking about today, stuff like our paper just got published in Inverse Problems. All right. So inverse problems and machine learning. So you all know what inverse problems are, but maybe like to kind of set the scene, to kind of like set the notation. So we want to consider inverse problems where we denote the for operator with A that maps some sort of desired solution U to our data B, and then obviously like the goal is to recover U given B, given data B. And so we are interested in 2 inverse problems here, or like in the application section later on, we will consider 2 inverse problems. So the first one is CT, where the for operator is the X-ray transform, and the second one is MRI, where the for operator is the subsample Fourier transform. All right, and I mean, as you all know, there are various ways how to solve inverse problems. One very dominant way over the last couple of decades is so-called variation regularization, where we try to sort of like approximate our original solution U star with a solution U hat that is a minimizer of such a cost functional, where the D is data fidelity, which kind of measures how close we fit measured data, and R is a regularizer that sort of like says like how regular is the solution, and then lambda is a regularization parameter which trades off those 2. And so like a lot of work has been into sort of like designing good regularization functionals, and then sort of people came up with a total variation or total generalized variation. And so here's one example for image denoising. And actually, so like these kind of regularizers, they work really, really well if you have something like a geometric phantom, which is fairly simple, but then they're not that great if you have like more realistic images, which maybe like a lot of like fine details and so on. But then it's like how to actually solve image problems. I mean, like this, like variation regulation framework, it's more like a mathematical framework. You still need an algorithm that computes such minimizers. And then, so like as you've seen, like in the previous talks, of like she outlined various ways, like gradient descent, ADMM, and so on, how to solve it. Maybe let's look at one of these methods in a bit more detail, which is proximal gradient descent or for backward splitting. And the algorithm goes as follows. So like first we do like a gradient descent step on our data fidelity, and then we do a proximal step on our regularizer, where the proximal is defined as this. And having this algorithm, we can then define a mapping phi that maps our data B to the limit of this algorithm. Assuming obviously kind of this limit exists, but like under like fairly mild assumptions on D and R, and on step size, we can prove that such a limit exists. It's unique. So like this makes sense. And so then, sort of like in practice, it works like you need to choose certain step sizes. You need to choose a regularization parameter, and then we have our mapping that maps for like B to our model solution U hat. And then we can prove that, for instance, I mean, as the noise level goes to 0, as the regularization parameter goes to 0 in a certain way, then we actually converge to our desired sort of like noiseless solution of our inverse problem. And then one option, also means the same as we have seen like in the previous talk, how you then can insert machine learning into such an algorithm is by taking this algorithm and essentially replacing this prox with a neural network. So here we do like even like one step further, where sort of like so even this like gradient descent type of step, see like being replaced. So like the neural network has 2 inputs. So our previous iterate UK and the gradient, and then like it spits out a new iterate. And then our solution mapping just like maps the data to UK, where we iterate this like a couple of times. And now one big computational benefit is now here this capital K is usually small, like 5 or 10. In contrast to the original algorithm, where we really are interested in the limits, we really want to have a lot of iterations such that this approximates well the model solution. And so then, like in practice, we want to learn parameters for these neural networks, such that the solution mapping now shouldn't be close to any model solution, but should be close to our ideal solution, like independent of the noise level. You always want to be as close as possible to the ideal solution. And so like this is how it looks like in practice. So like this is now like a bit more complicated version compared to what I've shown you on the previous slide. So here there's some memory S. So therefore, sort of like we have, and also here I changed notation a bit, so like what used to be x before, so like now is u. So we have basically like two variables that which is kind of like our current version of the image, now called u, and some memory s. Then we compute the gradient, put this all into a neural network, and this spits out the next iterate and the next memory, and then we can iterate this like a couple of times, and then we get our desired solution. Okay, so now on to equivariance. So first of all, so like kind of what is equivariance and why are we interested in this? And so like assuming, for instance, we are in the case of denoising, and then we have our data B. So what if we now observe not the noisy image B, but a rotated version of it? So then, like kind of like it's intuitive that ideally you have that the output, when you know like apply some denoiser to it, is then nothing else than the rotated version of the denoised B, right? So that kind of feels quite desirable. That is robust in terms of rotations. And so kind of this property you call that something is equivariant with respect to rotations. So here's some examples. So here we have some noisy image on the left. And so here we train a standard convolutional filter, and here we train something that will tell you like a second what it is. And so like both of these methods, they're able to kind of denoise these image of stripes very well. But like what happens when we now rotate the image of stripes? So during training time, there were always only horizontal stripes, but now during test time, we now look at vertical stripes. And now the standard convolutional neural network then kills all of this. And so you can see that like the noise is being spread out in a horizontal direction, right? So like it learns that it needs to denoise in a horizontal direction. So like it kills all the structure. Whereas now here the new method that we'll talk about in a second, so like doesn't do that, but like performs equally well, even though the image is being rotated. Okay. So, but now how do we get such equivariant mappings? And so, kind of like in the literature, what is usually being done is an approach that is fairly heuristic, and it's called data augmentation. So, if we have pairs of data, BI, UI, and in terms of denoise, you can think of like BIs as noisy images and UI as the clean versions. Then we augment the data to become sort of like we like rotate the noisy images and the denoise version. So our data set becomes much larger, and so we now have like all the possible rotations, whatever this now means, in there. And then we train on this new bigger data set. So this is very simple to implement, right? So like instead of choosing data points from the original set, we just like choose data points from the new augmented set. So that's so like any algorithm or any training algorithm that you've implemented before that works on this one very easily works on the augmented one. So that's great. It's potentially computationally costly, right? Since the data set now became a lot bigger. There are no mathematical guarantees that this will translate to new data, right? So like because I mean, for example, just like rotations, right? You have like an infinite number of rotations you potentially could have, and so like you probably like would want to like sample like a finite number, and so like what happens with rotations which are not in the training data set, but also I mean there's no guarantee that what you train actually will be equivariant even with respect to the rotations which are in the training set. And then another problem with this approach that it's not always easy or possible to implement this for arbitrary inverse problems. So like in terms of image denoising, it's actually like quite easy to do. But if you are in arbitrary inverse problem settings, so like what exactly does all of this mean, right? So because you can't rotate the data, right? So like if you think about the BI as case-based measurements in MRI, so like what does it even mean to rotate that? So if the BI are simulated from some ground truth images UI, then you can always do it, right? You can rotate the ground truth thing, then simulate what the BI would be. And so like in simulation setup, you can do it. But if your training data comes from a real scanner, then this is like by no means clear whether this is possible or feasible, right? So in this talk, we would like to do a different strategy. And we want to do equivariance by design. So we want to design neural networks which are provably equivariant, like no matter what the training data is, no matter how you choose the parameters and so on, but you're always equivariant. So it's like mathematical guarantee that you are equivariant. But then as a downside, this is obviously like not trivial to do so, and that's the reason why I'm talking about this today. Equivariant networks have been studied a lot in literature for image-based tasks like segmentation, classification, denoising. And so here at the bottom, you can see like a few papers which appeared over the last couple of years, but there are many, many, many more. So like in image-based tasks, like in computer vision, so this is a very, very popular approach, but sort of like so far hasn't been translated to inverse problems. And so maybe like from all the literature to highlight perhaps one paper, see the one by Weiler and Chaser, where a couple of the ideas and algorithms that we use later on are based on. Okay, so how does now equivariance and inverse problems fit together? Because I said before, sort of like, I mean, you can't rotate your training data usually, right? So what exactly should be equivariant? And so now if we call like A our for operator and phi our solution operator mapping from y to x. So now, for instance, to ask that phi is equivariant doesn't really make too much sense, right? So because I mean, like the x usually like are images, so like makes sense to talk about rotations, but then the y is the data, so like it's not really clear, sort of like what action you would want to have on y. So this is equivariant. Okay, so like where like in general like this so it doesn't make sense to ask for phi to be equivariant, but what we could hope to have is that phi composed with A, right? So this is a mapping going from x to x, going from image to image. So this might be equivariant. And so like in terms of like rotations, which means it's sort of like if you now apply your rotation to an image, then you apply A, then you apply the reconstruction. This should be the same as you first apply A, then reconstruction, and then the rotation. Okay, so here's now sort of like some picture of what this could look like, right? So here's right now some image of a pig here on the left. And so for these two things to be the same, kind of these two paths need to be equal, right? So like we have the image of a pig. We now rotate the image. Now here this is in painting, so we now sort of like have a mask, so we like don't observe this black square here. So a for operator selects everything but what is like hidden behind the black mask. And then our reconstruction here is a variation, a total variation in painting, which sort of like does a fairly fine job, right? But also like there's like no texture like on the mask. On the other hand, if we first sort of like observe a number of pixels, then we do the in painting and then we rotate, we can see obviously kind of like that the mask which we have observed, right, is different in these two things. And if the in painting isn't perfect, right, then these two solution paths would be different. So, like phi composed with A is not rotationally equivariant for variational TV in painting. And the reason is that sort of like something is not being observed here, right? And so like as long as your reconstruction isn't perfect, you might not be able to have that these two things are the same. But now, what about if we have a kernel? Because the problem here, right, is that we have a non-trivial kernel. And so, like, one question is, so like, what about like inverse problems where we don't have such a kernel, or where we have a reconstruction operator that sort of like finds the right elements from the kernel, for instance, such as like in corporate sensing. So perhaps there we might have a property that phi composed with A is indeed equivariant, but that's kind of future work. Okay, so like in this direction also then we can prove a small statement. So like in general variational regularization is not equivariant, but what we can prove, like if X is like some sort of like function space that represents images, for instance L2, and then our regularizer now called here J is invariant with respect to rotations, which mean that like if you have an image and you rotate it, then you have the same functional value. That is, for instance, the case as in total variation, total generalized variation, and so on. Then it turns out that the prox operator is indeed equivariant. So when you apply the prox to the rotated version of the image, that's the same as you rotate the prox of the image. And so therefore, sort of like in a learned gradient descent framework where we have replaced basically the prox operator with a neural network, now it's a very natural condition that maybe like as the prox was equivariant for like many of the models that we're interested in, so perhaps also like the network that we replace the prox with should be equivariant. Okay, so now equivariance revisited. So like everything I said before was about the special case of rotations. Now we want to make this a bit more abstract. So now we need to have a couple of definitions to be on the same page. So what is general equivariance? So equivariance is usually being defined with respect to a group. And so like for all those of you who have never have taken Algebra 101 or like it's a long, long time ago. So a group is defined in the following way. So like it's a set, right? So the G is a set. And where we have three axioms. So like on the one hand, and we have like an operation that acts between the group elements. And so like we need to have that the group action is follows associativity axiom, where so like it doesn't matter in which order we apply the group actions. Then also we need to have like an identity element such that when you apply the identity element to like another element, then you get the element back. And also sort of like every action needs to be invertible. So, but now sort of like the images that we're interested in, so like they themselves like don't form a group. So we now need to relate sort of like, for example, rotations to images. And so now we can define how a group acts on set X. And so now we have sort of like another action, sort of like how this works, which now takes a group element and an image X and gives you your image X as an output. So this needs to be defined, and this group action now sort of like also sort of like needs to have that if you apply the identity to an image X, then you get the image X out, and it needs to be compatible. So like how Gx on X needs to be compatible with the original group action. So, so by the way, so one word of caution. So now I use the same symbol here, like this dot and that dot, right? No, this dot and that dot. These are two different dots here, right? So this dot here is how a group acts on an image, whereas this dot is how two group elements act on each other, right? And so kind of like the group, so it's like how the group acts on images needs to be compatible to the group action, right? So like in this way. Okay, so now now as we like define what groups are and how groups act on images or any arbitrary sets, so like we can now like define what does it mean to be equivariant. So if we now have a group which acts on two spaces X and Y, and the group can act differently, so like on X and Y, or can act the same, if it makes sense. Then we define, we say like a mapping phi between X and Y is called equivariant, right? So like if the group action, so like as a group element acts on X is the same, and then we apply phi to it, is the same as the group element acting on phi of X, right? So that's what we call equivariant, and it's called invariant basically. So like if this action here is trivial, so if there's no G here on the left-hand side, then we call it invariant. Okay, so this was now like fairly abstract. So like how does it work in practice with images? So there are now various ways how groups, like rotations, for instance, and so on, can act on images. And so on the one hand, it can act on its domain. So group acting on an image is defined as that the inverse of the group element, so acting on the input of the image. Right, so like this, we can, for instance, then like define rotations and scalings and so on of images. But then so like there are like other ways. So here are a few examples, but I don't want to go into too much detail here. But then the group can also act on the range, right? So like that, the group acting on the image is defined as now the group acting on this element here. So like, did I not give this a name? I don't know, like this before, like in Y, right? So like that you evaluate first at X and the group acting on this one. Okay, but also, and this is something that we will use in the following, the group can act on both the domain and the range, for instance, kind of like in this way, basically like composing these two things together. Okay, so, and I mean, there are many groups, and so but here we are interested in a particular group, and this group we call G bar. And so this this group is composed of, let's say, like two subgroups, or like two groups itself. And so like one of them is a subgroup of the general linear group. So you can think of H as like rotations, for instance, and then the Rn comes in for translations. So now sort of like we have that the G acting on X is we rotate the X by some rotation matrix from H, and then we apply some additive shift to it, so we translate this one. And so now sort of like having such a group, we can now sort of like have that the G acts on an image U, which is a function, right? And such as that we take the inverse of the element acting on X, right? So this is how the inverse looks like if the G acts in this way. And then sort of like now here there's a pi coming in. This is called a group representation. So like that the pi of the rotation matrix should act as the output of U. And sometimes we will choose the pi to be equal to the trivial representation, where that's basically, I mean that this one disappears. Sometimes we do, for instance, like if the output of U is a vector field itself, right? So you do want this vector field to be rotated. And so here is an image here taken from Weiler and Chaser here at the bottom. So for instance, now so like if we have an image and we rotate it, So like if the values of the image are scalars, right, then we like might not want to do anything with the values themselves. But if the values are vectors, so like then so like in order to rotate the vector field appropriately, we might want to have that we also like rotate the vectors as we rotate the vector, like the domain itself. Okay. So now we can prove like a more general version of the theorem that I've shown you earlier, now like for like general groups and not just for rotations. So if G acts isometrically on X, meaning that like G acting on U, so like the norm of this is the same as the norm of U, then if we have some function J which is invariant with respect to the group action, and if J is well defined and has a single value prox operator, just like for all of these conformities to make sense, then the prox is equivariant with respect to the group action, in the sense that sort of like the group acting on the group element acting on U, the prox of that is the same as group element acting on the prox of U. The proof does indeed generalize to variation regularization. So like the counterexample that I had before with the in-painting, so like one can prove this for variation regularization if A itself is equivariant, like if it makes sense, and if it is indeed equivariant. And so kind of like if you have a kernel, right, then you can always with your group action shift something to the kernel, right? So like if you have a kernel, then A will like never be equivariant. Okay, so how does this now work together with neural networks? So how do we get equivariant neural networks? So like first of all, there's actually like a big calculus, sort of like with equivariant mappings. So if we have two mappings which are equivariant, then their composition is also equivariant. We have that if we have two mappings which are equivariant, then the sum is equivariant, and the identity function is also trivially equivariant. I will show you on the next slide that there are linear operators which are non-trivial and are G-bar equivariant. Like this G-bars is like this like roto translation group that I've shown you on the previous slide. Then biases are equivariant as long as the bias itself is invariant. And there are nonlinearities which are G-bar equivariant. Again, I will show you in 2 slides. And so therefore, so like with all of these building blocks, we can now construct neural networks in the usual way, right? So for instance, we can have one layer which is equivariant, and then like n layers, and then we compose this together, and we again get something that is equivariant. Then our standard feed-forward neural network, we can choose, like, let's say, like the nonlinearity and the A and the bias in the ways this one is equivariant. And the same with the ResNet, right? Since the identity is equivariant and the sum is equivariant. So it's like as long as we can construct such like a feed-forward type layer, then again we can construct bigger neural networks which are all equivariant. Okay, so now it gets a bit technical here. So like now in order to simplify things, this is now for the trivial representation. The formulas for arbitrary representations you can find in our paper. And so kind of like in a nutshell, sort of like the take-home message is that there are non-trivial linear operators which are G-bar equivariant as long as, and these are the convolutions, as long as the kernel satisfies some additional constraint. So in practice, so sort of like in more detail, so like how this is, so like if we have an operator acting between 2 spaces, for instance, could be L2 or something else, and this phi is a linear operator defined in this way, then this is G-bar equivariant if and only if there is a small k. So like now, so there's a capital K, right? Has 2 inputs, x and y. This small k has only 1 input, right? So like if there is a small k such that we can represent the linear operator as a convolution, and in addition, this k needs to be H invariant. Right, and you remember like H is a subgroup where you can like think about as like rotations, for instance. So like for all elements R and H, we need to have that however so like X being first like rotated as a special case, then sort of like this needs to be the same. So like for instance, like if if you think about a K, for instance, like if you have, let's say, like a Gaussian kernel, right? Then that would be indeed invariant with respect to rotations, right? And so like overall the convolution operator that comes from it then would be G-bar equivariant. Okay, so for nonlinearities, like the story is similar. So like again, so like things are rather complicated for non-trivial representations. Again, Please have a look in the paper if you're interested. For two representations, things are still a bit complicated, but much easier. And so, like in a nutshell, there are nonlinearities that we can pick. So, like in more detail, so like in the literature, there are two nonlinearities that you can choose. And so maybe like this one is not going to like too much detail, but maybe like let's talk about this point-wise, component-wise nonlinearity. Since this is the one that we also usually choose in practice, right, where the nonlinearity usually acts component-wise on vectors. That analog for continuous images then will be of this form, right? So it's a nonlinearity acting on an image evaluated at some x, right? So this now, first of all, it acts point-wise, right? That's what this equality means. And now, so like if now this x is a vector here, then sort of like it's also like should act component-wise, in the sense that sort of like its ith component is nothing else than sort of like again some scalar function applied now to this scalar value xi. Okay, so both of these nonlinearities are G bar equivalent. All right, let's talk about some numerical results. As I said before, so like we want to have, or we're looking at two application areas, CT and MR, and so like a little bit more detail on exactly what we have been looking at. So like we look at two open data sets. So like here, there's an open data set which is coming from low dose CT, and so here's like this is now how our ground truth images look like. And so now then we simulate some data based on this, and if we now apply a feedback projection to it, then this is how it looks like. So this is like some feeling of sort of like how much undersampling and noise we've added to it. And similarly for like MRI, we're talking about like undersampling. And again, if you look at the minimal norm solution, this is how it looks like. So like this gives you some indication of like how much undersampling noise there is in the data. And so like both of these data sets are, I would say, like medium size, right? I mean, they're like fairly small compared to things like ImageNet, but then they are like of like proper size, like a few thousand images. And so we use here like 5,000 images for training, 200 images for testing, and 1,000 images for validation, and the same for the fast MRI dataset. Okay, so here's some results. So basically, so like what we compare here are two different methods. So these like learned proximal gradient descent, and once the neural networks involved, they are convolutions. So here now we call them like ordinary convolutions. So they are translationally equivariant. And what we call here equivariant, these are where the convolutions are, where the neural networks are equivariant with respect to rotor translations. So these are the other two methods, and here on the right you can see the ground truth. And so like what do we see from these results? So first of all, we see that sort of like SAM is maybe like about the same, maybe slightly higher for the equivariant one. PSR is quite a lot improved. But maybe like more important than looking at these numbers is looking at the images directly. So like the results from the equivariant, the rotor translation equivariant neural network. So like they had like much better results. Like there's like a lot of like cloudiness going on here. This is like a very like nice result. And can you see this on there? Maybe not so much, but here, for instance, I mean, like another area that I could have highlighted. So there's some spurious artifacts here at the bottom that actually like look fairly realistic, like a bit of like dark areas that which you can't see in the rotor translation equivariant neural network. Okay, some quantitative results. And so here the take-home messages I would say are a bit similar in the sense that sort of like the rotor translation one works like a bit better. And so like in more detail here on the x-axis with the training size. And so here on the left in total are the upright test images. So like the test images just taken as they are from our database. And here on the right are the results for if we take the test images and artificially rotate them, right? Looks like it's all about equivariant with respect to rotor translations. And so what we can see here is sort of like the equivariant one here in blue, the ordinary one in orange. So if we have like a large amount of training data, then actually like it's like doesn't have like much of an effect. But like the difference is really significant once you go to like small training sizes. And now if we apply everything onto the rotated test images, there the difference is bigger, right? So even for like small training data sets, the ordinary one breaks more easily, but also kind of like the transitions of like when the equivariant one is favorable compared to the convolutional one, sort of like is already here at like 100, 200 training images. So here we can see like a difference on the rotated test set. The story for MR is quite similar. So like I don't show you any images here, but let's look at the quantitative results. So that like overall the rotation translation one seems to be better than the ordinary one if you like don't have that much training data. But here now the difference, on the one hand, the difference is smaller as we have already seen on CT. I don't know why that is. It's probably an open question. But there's another thing that's very subtle that our reviewers recognize from paper that we haven't even seen ourselves. And can you see it from here? So maybe like if we focus, for instance, on training size 10, can you see that this bar is higher than this bar? Maybe I should have drawn a line. Can you see this? So this is kind of like a bit strange, right? So like, why would both methods work better on the rotated test images than on the upright test images, right? Because they are supposed, like at least in a continuous sense, they are supposed to, at least the equivariant one, kind of like they're supposed to work kind of similar or the same. So this is a bit sort of like surprising, and we have made some experiments to look into it, why it is. So we were speculating first that this is because when you rotate images, when you rotate discrete images, you need to interpolate them. So it also has a smoothing effect on the images. So we were like numerically testing this. So now here, so like on the in the left graph, you can see the equivariant one, on the right the ordinary one, and now the blue one are the unaltered images, and the orange one is rotated. But what I mean with rotated is that we rotate it by a certain number of degrees and then rotate it back, right? Which is just like we have done twice in like some interpolation, and we've basically done exactly like the same kind of smoothing that you would do via rotations, but there are no rotations in the end. And what you can see here with the results, that sort of like the blue one seems to lie significantly underneath the orange one, meaning that the smoothing coming from rotating back and forth actually, so like both methods improve when you smooth the images this way, which is kind of like it's an interesting observation. Okay. So this I would like to conclude the talk. So first of all, I think one of the main take-home messages is that there is no need for data augmentation, right? So we can have like mathematically guaranteed equivariant neural networks by building them carefully. Then what we've seen is that solution operators for image problems, they generally may not be equivariant, because like it may not even make sense to talk about equivariance, but the proximal operators, they are usually equivariant. One thing that I didn't talk about before, but I would like to highlight it nevertheless. So like that this equivariant framework that I presented is computationally very efficient. So like with at runtime, these are nothing else than convolutional neural networks. These are exactly the same, just like that we have chosen filters more carefully. So like during training time, we have needed to spend like a bit more extra effort, but at runtime, it's exactly the same. And then sort of like this can be useful for like many applications. We've seen like CT and MR. And so like I would say like two take-home messages there. I think if you have a lot of training data, we don't see much improvement there. But like if you have like only like a few data points and you are interested in robustness, then this can be for you. And then so like in the future, there's like basically with like any research project, right? Like once you get started, so like the more you work on it, the more open directions there are. So like first of all, so we're interested in like in other groups. So we now focus on rotation translations. But there are clearly other groups of interest. So for instance, like scaling of intensities. So like what happens, let's say, for instance, if you change the units of an image, right? Then let's say like if you go from, I don't know, meter to millimeter, right? Like it's like nothing else than like a global upscaling. So if you want to be equivariant with respect to units, this would form like a group. Then you can have like a scaling of the domain or some affine transformations of the domain. Then other image problems are clearly of interest. So I highlighted compressed sensing and trivial kernel because they're sort of like maybe kind of like this solution mapping composed with a forward operator, maybe equivariant. And then obviously sort of like higher dimensions are of interest, like make this computationally feasible for like 3D imaging, but also sort of like maybe like there are some groups which are sort of like particularly suited to like dynamic image problems and so on. And again, so like if you want to see like more details, this is our paper. Thank you very much for listening.
Thank you, Matthias, for this awesome talk. Again, you can either write questions in the chat. I'll be looking at it, or just unmute and ask. There is one question from the audience. Martin?
Yeah, thank you. Thank you for the nice talk, cool stuff. I have probably two questions, if you allow me. So the first one was with your TV example.
Yeah.
So if I got it correctly, because obviously normally TV itself, or the RF model is sort of rotation invariant, but because, so basically your A here is not equivariant, right? That's basically what causes the issue with, and you said something like that every kernel basically, or you have.
So every for operator that has a non-trivial kernel has this property. I mean, like, obviously, like, it depends on the groups that you're talking about as well, right? But like, if you think about like rotor translations or translations only, so like if you have a kernel that you can move into, right? I mean, so like now, if you are in a more complicated scenario, let's say like undersampled CT, right? So what does it mean to move into the kernel, right? So like, not sure, maybe like there's some CT experts in the audience who can tell me what this means. But kind of like if you can transform your image or like some image that you can transform into the kernel, then there's no chance that you can be equivariant.
Yeah, I see. And my other question, could you think of, let's say, having data samples for which you think they show some equivariance in them? Could you try to infer an equivariance rather than using equivariance to basically make reconstructions so better or rely on fewer data samples? Could you also try to infer?
You mean to learn the group from data?
Yes.
We haven't thought about this. I think in some of the papers, I think they mentioned this, but like not that they have done it, but they mentioned that this would be of interest. Not sure what. So like my feeling is in computer vision literature, with like a super active topic in computer vision literature, my feeling is probably some people have looked into it, but I wouldn't know a paper.
Do you see any technical issues or anything that makes it sort of more complicated trying to infer? I mean, in terms of the optimization, the group, or do you think it could be relatively straightforward?
I mean, you would need to think about it. I mean, first of all, I mean, how would you learn this, right? So suppose you would need to parameterize the group, and you would want to do it in an unparametric way, I suppose, as possible, because you don't want to enforce the structure of the group. So from the top of my head, I have no idea, but I would be very interested in this. But I don't know. But it's a very, very interesting question, and the things of like, I think like rotor translation, I think are quite intuitive. But like, again, like if you are in a very complicated data set, maybe like we humans shouldn't tell the machines of like what are interesting equivariances, but rather learn from it. Yeah, sounds interesting, but I don't know. Yeah, thank you.
Okay, I think.
Yeah, thank you very much for the very interesting talk. I have a question concerning the equivariance. So I think it got already a bit obvious in your last example. I mean, the problem is if you have like your group action on the image and you're in a discrete setting, then rotating and rotating back is not giving you the identity as it should be with this group formalism, because like if you take the inverse angle, it will be 0 in the identity transform. So does this mean that the network is designed in such a way that it's only equivariant in a continuous framework, or because like there's this discrepancy between working on discrete images and like that it doesn't really fit?
Yeah, so I think that is up to you, I would say. So there are groups for continuous images, but there are also groups for discrete images. So for instance, when you think about translations, right? So like if you were to translate a pixelated image by exactly 1 pixel, right? Then sort of like this is also kind of like a group, right? And you can like the inverse is you like move it back 1 pixel. And so if you like to think discretely, so like there are groups of this form. So I personally like to think about these images as continuous images. So like therefore, like I'm more interested personally in continuous groups. And so therefore, sort of like basically here. So for instance, like with the rotor translation that we have done here, so like there, I mean also there, so you could have, for instance, like a subgroup of all rotations that moves by, let's say, like 90 degrees, right?
Mm-hmm.
And then we have no problems, it's like working on a pixelated grid. But so like I personally sort of like I don't want to, let's say, like overtune towards pixelated grid, because maybe like in the end of the day we want to go beyond pixels, finite elements, whatever, right?
Like even if you do the rotations and your image is rectangular and you're rotating by 90 degrees, then the domain size will change.
Yeah, fair enough.
Not too...
But then you can have like 180 degrees if you want to. But it's also like I don't want to advocate this type of thing, but you can do it, right? I mean, like, it does exist. So like I personally think that sort of like it makes more sense to think about it continuously. But then obviously sort of like then some of these equivariants that I talked about, right? When then discretize, you can't expect that that sort of like the discretized system is 100% equivariant anymore. If you have discretized, it's a continuous world was equivariant, then obviously there is some error when you then do the discretization. But you can still hope, right, that if you make the discretization finer and finer, that you can like converge to the continuous setting.
Then maybe just one more question with respect to this. So you're always using images on Rn, right? So you're having somehow a domain which is itself invariant with respect to your rototranslational group. So you're not having like a domain with boundary or something which would be not itself invariant. So because like the difference is if you're just using a square and you're rotating it, then it won't match anymore. And if you're using Rn, I mean, you can shift it, you rotate it, it will be the same space. So it's
like, and with Rn, you mean like Rn by n?
Yeah, you're just using the whole space. So you're using the whole Euclidean space, nothing with a boundary.
Well, I mean,
what would happen is like if you have something with a boundary and you do a shift, like you eventually come out of the region and you somehow have to pad something where you don't know what information is. And like if you just think of going once completely out and once completely back in, you will have just the padding information back in. If you have a domain without boundary, that cannot occur.
So we do have a boundary, right? So then we need to talk about boundary conditions, right?
Okay, yeah.
And so kind of here, so like in the numerical examples, I'll show you here in the end, right? Okay, so like here also, I mean, these are like cropped, right? So like there's like a lot of blackness around it, right? So like we use here like zero boundary conditions. And so like since the image of interest, like since the region of interest going so far away from the boundary, we haven't numerically observed any issues there. But obviously sort of like here now, this one sort of like it's not, I mean, so yes, you could kind of move out of the field of view, right? And then if you then were to move back, then you have lost all your information. We haven't observed any numerical problems in this regard, but also I believe because kind of like the boundary was quite far, because I think like, I mean, these are the cropped images, right? So like I think the original images, I mean, they go maybe until here or something, right? So like, there's a lot of blackness around them if you don't crop them. Yeah.
So as I understand it, your proximal operator and your regularizer are equivariant, but your networks aren't, and you explained how that's not necessarily a meaningful thing. So what sort of, do you have any thoughts on what sort of theoretical results you could put on these networks to say what, you know, because you're seeing they empirically perform better, but how would you couch that in a theoretical statement?
That's very, very difficult. Also, I mean, like maybe like one thing that is quite important here that I think, I mean, the main message of the talk is really about equivariance, and then we used it in a learned, so like in an unrolled proximal gradient descent method as a prox operator. But then you can use this also in like many other ways, right? And as we have seen, for instance, I mean, this morning, but maybe like perhaps like in my view, maybe like more interesting, so like the talk we had on Monday about this deep equilibrium methods, right? Also there you have like the same structure. So I think if you want to say something theoretically, it's like, because I think that these unrolled algorithms, I think they are not very amendable to theory, right? So therefore I think so like, so if you have some theory, for instance, like about the deep equilibrium methods, where I think also like, I think the speaker on Monday, I think so like she like didn't have any results, but I think that maybe that is an area where you can have some results. And then I think once you have them, maybe then you can say more when you have equivariance.
You even with the TV, you're saying it's not equivariant. The system is not equivariant.
The variational regularizer.
It's not equivariant. If you're in all cases, if you don't have an inverse model. So when can you? I mean, I'm just trying to think how one would articulate the theoretically where the gains are coming from in the in putting an equivariance on a regularizer rather than something else.
Yes, it's difficult. So I mean, like one thing that kind of like in the computer vision literature, sort of like what's usually being referred to as sort of like sample complexity. So like that potentially sort of like so I mean, as you have more structure on the network, you have a better sample complexity that you need fewer. I mean, we empirically observe this, right? But I also make this like not theoretical. So that might be an option, but also like then the relation to the inverse problem, as in only use it as a building block for the inversion methods. That's quite difficult, I think, to make that step forward. But if you have any ideas, please do let me know.
Okay. Very quickly, because we should start in a minute.
Yeah, I was just wondering, how do you, in training, how do you enforce that your kernel has the, you show the theorem that says there exists one, but how do you actually do this for a discrete kernel?
So there are various options in the literature, and so what we follow is sort of like oops, let me go back. What we follow is is a software framework proposed by Weiler and Chaser, and so like that they call it steerable convolutional kernels. So like you have like some sort of like parameterizations of the kernel, and then so like for all of these parameters you have a certain equivariance, and then you can learn these ones. So like I would like refer, I mean, so like you can also check out our paper, or the original source would be like Weiler and Chaser, if you want to learn more about this.
Okay, thank you.
Thank you. Oh, we have something in the chat. Okay, I think Ozan is posted a couple of papers, links on archive for everyone to check out on this. Okay, then. So I think since we have only 3 more minutes to the next speaker, we thank Matthias again. Thank you very much. Okay, so Thomas, are you there? And
yes, I'm here. Can you hear me? Hello. Hello.
If you are talking, we can't hear you.
I could hear you, Thomas.
Aha, okay. So it seems it's not on my side the problem.
But I'm not in the auditorium. I'm calling from home.
So you can hear me, Ozan?
Yes, I can hear you.
Okay, then okay.
Okay, so Ozan can hear you, but we still cannot.
Okay.
No.
That was strange. I wasn't able to hear. That's a new one.
We can see your slides, but still cannot hear you.
Thomas, is your microphone enabled?
Yes.
We now see you.
You can hear us, Thomas. Just give us a thumbs up if you can hear us. Cool. Just check your mic is enabled.
Second.
So
So we are adding that.
people in Zoom can hear me, right? People on Zoom can hear me.
Yes, we can hear you.
Thank you.
Try now.
Try
Hello?
again. Oh, yes, now we can hear you.
It works. Okay, great.
Do you just want to close the chat window, please?
Oh, yes.
yeah, thanks.
Just a second. Okay. I think we are actually perfectly on time. I mean, we skipped a 10 minutes break here, but it's okay. I guess we can start.
Yes.
So we are now at our last talk of the morning. Our next speaker is Thomas Pock. He is professor of computer science at TU Graz since 2014. He got his PhD from the same university in 2008. And then after a short postdoc at the University of Bonn, he returned there. Today, he will talk about variational modeling meets learning. So please.
So thank you very much for the introduction. Hello, everybody. Welcome to my presentation. As was said, I'm talking about variational modeling meets learning, and this is joint work with a number of people: Karl Kunisch, Antonin Chambol, Alexander Effland, Erich Kobler, Thomas Pinitz, and Martin Zach. So I will start with the very general framework about models I'm talking about, and it's basically more or less the same kind of models we've already heard in the previous talk. So it's energy-based or also variational models. And my definition here is that we have a pair of output and input variables. So let's call Y to be our input, a noisy image or a set of stereo images, or measurements in a K-space or a sinogram, and X is the desired output, which would be the reconstruction of an image, for example, the denoised image, the reconstructed image, and so on. So in variational models, as opposed to different models that are now popular in machine learning, like feed-forward models, the task of inferring our output X from the input Y is defined by an energy minimization approach. So we usually define X hat, the desired output, to be in the set of minimizers of our energy that somehow assigns an energy to the configuration of X and Y. And of course, we are interested in finding efficiently a minimizer of an energy. If the energy is convex, then we have good hope to find a global minimizer. If the energy is non-convex, then we would already be happy with a local minimizer or a stationary point. So this basically depends on how the energy is made. It could also be discrete, for example, in case of Markov random fields, or it could be a continuous energy. So when you look to the literature, energy-based models are not only popular in image reconstruction, inverse problems, and so on, but they also are popular in general machine learning recently. And I think this is because they come along with many interesting properties. So first of all, you can think of energies that are simply handcrafted. So this is what people were doing in the first days of variation models for imaging. It's more or less physics inspired. So very often formulations that have been known in physics have been translated to image reconstruction, leading to different regularizers, Tikhonov regularizers, total variation, and so on. But energies, and this is what is now popular, can also be learned from data using supervised learning or even sometimes self-supervised or maybe also unsupervised learning. One of the advantages of energy-based models is that solutions can be characterized by optimality conditions. For learned models, this might be difficult, so we are not that far. But for handcrafted energies, for example, referring to the famous Mumford-Shah functional, which is a particular type of handcrafted energy, the optimality conditions really allows us to characterize how a solution is made of, for example, triple junctions. If the energy is non-convex, or even in a convex case, if it's non-unique, then energies can allow for multiple solutions. For an optimizer, this is a bad thing, but sometimes it can also be useful that we have multiple solutions. Also in energy, also in nature, where also nature performs energy minimization to some extent, sometimes you can be trapped in locally minimized, for example, playing around with soap films. And if the energy is connected to some measure, then you can, of course, the energy you found in energy minimization can also provide a quality measure. For example, the mean squared error is directly connected to PSNR values, or for example, the total variation is connected to the perimeter, and so on. It was also easy to introduce additional latent variables. For example, I have it on the next slide. In the Mumford-Shah functional, you can easily introduce latent variables, for example, a discontinuity set, and for which we can minimize it out. So the original energy E of X and Y is given by the minimizer with respect to set of the energy, also involving the latent variable set. So here are just 3 examples of energy-based models, of popular energy-based models in computer vision and machine learning. In discrete optimization, usually the energies are motivated by map inference of Markov random fields. So here I have a typical energy formulation where we try to find the labeling of an image, which is in some labeling space. So on the right-hand side, you see a depth labeling of a scene of the Kitty data set, and you have assigned different costs for labels, theta I of xr, but you also have defined costs for pairs of labels of neighboring points. And this type of energies have been used a lot in computer vision for different tasks like stereo, optical denoising, image segmentation, and so on. On the other side, in continuous optimization, one of the prototypes of variation models that have attracted a lot of interest is the famous Mumford and Shah functional. here X is a continuous function, and the idea is given some input function Y, for example, noisy image, we would try to find a piecewise smooth approximation X. And this piecewise smooth approximation is obtained because we are penalizing with this quadratic energy gradients in the image X. But we also have these latent variables, the jump set X, so where we have additional costs for jumps, and this leads then to piecewise continuous approximations. On the right-hand side, you see the famous crack tip, where you nicely see the discontinuity, which is the crack, and the smooth approximation around the crack. Also in machine learning, energy-based models have been used a lot. For example, the famous Lasso least absolute shrinkage thresholding regression model by Dicharani. And here the idea is that we have given some matrix A, and we would like to approximate with a sparse number of atoms of A our given measurement or our given signal Y. And this model has been shown to be quite robust, and this is mainly induced by using the L1 norm. So there's also an interesting and nice link, and I think every one of you knows that, between energy-based models and Bayes' theorem. So a typically energy-based model for inverse problems in imaging looks like this. We have a sum of two terms, a data fidelity term, here, for example, least squares term involving some forward operator A, and this penalizes quadratic deviations between our measurement Y and A times X. For example, Y could be measurements in a K-space, in case of MRI, X would be the reconstructed images, and A is a Fourier transform, or additionally is a masking operator that transforms the reconstructed image X to the measurement space. And the second term is the regularizer, and this is usually used in order to impose prior knowledge onto the solution, for example, smoothness or sparsity or whatever kind of prior is useful. And of course, when we talk about learned energy-based models, then very often this regularizer R of X is learned from data, and this is also what I will talk about today mainly, but also a little bit about learning the data fidelity term. So now, when we now compare that to a posterior formulation from Bayes' theorem, where we know that a posterior P of X given Y, so the probability of inferring a solution X given measurements Y is proportional to the likelihood P of Y given X times the prior P of X. Then by taking the negative log, we can easily see that the data fidelity term corresponds nicely to the negative log of the likelihood, and the negative log of the prior nicely corresponds to the regularizer R of X. Sometimes this might seem a little bit artificial, but for example, when we talk about generative learning of regularizers, it turns out that this relationship is quite useful. So of course, a big and interesting question is, how can we train energy-based models? And I've tried to survey a little bit of literature about that and present you the most prominent approaches. So let's assume we have given now in a supervised learning setup output-input pairs xn and yn. So we have samples yn and given ground truth reconstructions xn for that. And we assume we have a data set with a certain number of those pairs. Then we consider an energy. Now we are already in a learning setup, so where we try to learn some parameters of a parameterized energy E theta, and these parameters are just stored in this parameter vector theta here. So the basic and most intuitive idea is actually called contrastive learning, and this dates back to Hinton in more machine learning setup. We try to find the parameters theta of the energy such that the energy should be low of corresponding ground truth input output pairs and should have high energy on contrastive pairs with some chosen X tilde. For example, we would like to have that the energy is high for noisy reconstruction, that it should be low for the ground truth reconstruction. So therefore, we set up this optimization problem. We minimize the sum of the energy with respect to theta on corresponding ground truth pairs, and we maximize the energy with these contrastive pairs. Of course, here the question remains, how should we choose this X tilde? Can, of course, artificially generate different contrastive pairs, but maybe there's a more principled approach to that. And actually, when you look to classical maximum likelihood, which is now back to the Bayesian interpretation of energy-based models, and you minimize the negative log likelihood on a database, you find a formulation like this, where the first term, as you see, is exactly the same as in the contrastive learning. But the second term, here the sum of contrastive pairs is now given by the soft minimum of all possible reconstructions X. Of course, this is untractable because here we have an integral over all different reconstructions X, but at least it gives you an idea how this relates to contrastive learning. And interestingly, if you now compute the gradient with respect to theta, the first term we see it's the same, but the second term actually turns out that we get a sum over samples sampled from the current model, from the current Bayesian model. Since this soft min is intractable, people were trying to approximate this, and one of these most successful approaches is that you replace this soft min, this contrastive soft min term here, by trying to find examples that have low energy but are far away from the corresponding ground truth reconstruction. So we try to find these worst case examples that have low energy, for which we would like to push up the energy, but they are far away from the ground truth, according to some function delta. Delta is usually some sort of loss function. Another approach that is quite popular now, and this is so-called adversarial training. So here the task of finding contrastive examples is formalized as a minimax game. So it's a game between trying to fool the energy. And the idea is the following. The first term is exactly the same as before, but now we're additionally learning a generator that generates the contrastive images. The generator has some parameters theta as well, and the generator tries to generate from a given noise example, Zn, a noise vector Zn, images that have low energy, because when we maximize with respect to theta, we maximize the negative energy, so we minimize the energy with respect to this theta. So it tries to find examples with low energy, but at the same time, we also minimizing with respect to theta, so we try to push up the energy. And if you're familiar with generative adversarial networks, you might see, okay, this energy is nothing else than the discriminator. So energy-based models and discriminators in adversarial networks are quite related. The last class I would like to mention is bi-level optimization, because this is the one we use most currently. And here the idea is it's also quite intuitive. These x hat n are minimizers of our energy-based models, for some given by n, and we try to find the parameters theta of the energy-based model such that we minimize some loss function. Loss function is usually quadratic or L1 norm that penalizes distances between these minimizers with respect to the ground truth xn here. Since bi-level optimization is hard, it's a very hard optimization problem. A popular approach is, and this is what we heard in the previous talk, unrolling. So we simply replace the minimizer or one of the minimizers, if it's a non-smooth energy or non-convex energy, we replace it by the kth iterate of a method that is guaranteed to converge to a minimizer or a stationary point of our energy. So here we, in the loss function, we replace x hat n by the kth iterate, and therefore it can be seen as a kind of a approximate bi-level optimization. Of course, sometimes it's also popular to consider different parameters in every iteration, but then it no longer corresponds to a bi-level optimization problem. But then it becomes more similar to classical feed-forward deep networks. So what about bi-level optimization? So if the energy is strongly convex and twice continuously differentiable, then one can make use of implicit differentiation and to compute the gradient of the loss function with respect to the parameter vector theta. And I have plotted here the formula. So you see you need first solve the energy, get x n hat, that is a minimizer for particular theta. Then you need to compute the Hessian, invert the Hessian, and compute this formula from that. And basically inverting the Hessian, if you write it down as, for example, as a conjugate gradient, it's nothing else than a back propagation. So you see this back propagation or implicit differentiation shares a lot of similarities. Recently, together with Antonin, we have also considered a bi-level optimization approach for less smooth energies, which come along in the form of a convex concave saddle point problem in this usual form. And now the learnable parameters are hidden here in this linear operator K. And we have developed a piggyback primal dual algorithm that simultaneously solves for the minimizer of the saddle point problem, for the corresponding primal problem of the saddle point formulation, and its adjoint. And it can be shown that actually, again, if the energy is twice continuously differentiable, strongly convex, you have linear convergence on the primal problem, and at the same time, you have linear convergence for the adjoint problem, just with a slower linear convergence rate. And the nice thing here is that we don't need to first minimize energy and then compute the adjoint in order to get derivatives. We can do both at the same time, and this is basically seen as a minimization with errors in the gradient. So as I mentioned, unrolling is also popular, and one possible interpretation, and this is something we did together with Karl, Alexander, and Erich recently, that it can be interpreted as early stopping a discretized continuous time gradient flow on the energy model. So therefore, we can make use of optimal control and put this into an optimal control framework. It also provides a nice link to deep learning, and in particular to so-called residual networks. And for example, the stability of this unrolled iterative solvers is confirmed by ODE theory, for example, the work of Hauer and Rutotto. So when you look to one step of this learned unrolled gradient method, you see that, for example, if your regularizer makes use of convolutions, you have here convolutions, here you have the derivative of your nonlinear potential in your regularizer, which can be seen as the activation function, and then again a convolution by the joint operator. And additionally, you also get information from the misfit in the data fidelity term. But you see, this very much looks like a feed-forward network. So what about regularizers in imaging, which we now will try to learn? Of course, the question is, what are good regularizers? And in the early days, the most simple regularizers were based on just penalizing intensity variations, basically gradients or second derivatives, edges, and so on. And one of the most famous one is the so-called total variation. I guess everybody of you knows the total variation. And this is based on just horizontal and vertical differences and taking the mixed L2, L1 norm out of that. So now you can check, for example, again, referring back to the Bayesian approach, how much does this fit to the true statistics of natural images? So we could, for example, just compute on natural images the histogram of horizontal differences and take the negative log of the histogram. You would find a function like the black curve here, and comparing this negative log of the histogram with the potential function of the total variation, we have seen this relationship. And in 1D, this is just an absolute function. You see that it provides some sort of fit, but it's not a perfect fit. Of course, then you can start to replace the L1 norm with for example, a log student t distribution or generalized exponential, then you would get a slightly better approach. So the total variation can not only be used for image denoising, but also for deblurring, for MRI reconstruction, for optical flow, for stereo computation, image segmentation. Image segmentation, therefore, because for binary images, the total variation is known to be equivalent to the perimeter of the set represented by the binary images. And if you have multiple binary images, multiple labels, multi-label image segmentation, then of course this corresponds to the total length of all these segments in the image. So what about image inpainting? We have in the previous talk already seen that total variation can be used to inpaint part of a pig. So here it's even in a more simple setup. We would like to inpaint the straight discontinuity here. And since the total variation minimizes the perimeter, we know that actually the solution should be a straight discontinuity. So inpainting is performed in this gray shaded disk area. So now if we minimize a standard discretization of the total variation, we typically find results like this. For grid aligned edges, we are quite satisfied. You see the performance in measured here in decibel is quite high, so you cannot distinguish it by the human eye. But for some orientations like this one here, we really find very blurry discontinuities, and this is simply the case because the total variation based on horizontal and vertical differences induces some anisotropy into the solution. And this is also related to the equivariance we have seen in the previous talk. So for standard applications, just denoising or optical flow, I would say this slight non-equivariance of the total variation doesn't play a too big role, but there are advanced applications where also some sort of the total variation is used in a higher dimensional setting, like the convexification of the Mumford-Shaw functional or the convexification of Euler's elastica. Really, the discretization of the total variation plays a major role and can make a difference between working and not working. So therefore, we have been interested together with Antonin in how can we learn optimal discretizations of the total variation that ensure some properties like rotational invariance and so on. So therefore, what we did is we defined a family of discrete total variations for pixel size of size epsilon squared. And actually, let me refer you to the most right formulation. This is a typical dual definition of the total variation. So here we have the primary dual pairing between the dual variable p, which is a vector field for 2D images. Here we have the finite differences operator with the discretization epsilon applied to the image u. And of course, we need to scale the energy by epsilon squared. And usually in a dual formulation of the total variation, there's a pointwise restriction of the dual variable that the norm of the vector of the dual variable should be less equal than 1. And here our definition is that we say, okay, since applying this norm constraint to the dual variation is the source of the slightly wrong discretization, we introduce here filters, convolutional filters that interpolate the dual variables at particular positions on our pixel grid. So that means we apply this constraint to interpolated variants of the dual variation. And now it turns out that actually as epsilon goes to 0, if we ensure that the filter coefficients of these convolutional filters sum up to 1, so these guys are the coefficients for the first component of the dual variable, these are the coefficients of the filter for the second component of the dual variable. If we can make sure that they sum up to 1, they can even be negative, but they need to sum up to 1. And we also need to make sure that they are uniformly bounded. Then as epsilon goes to 0, this sort of discretization gamma converges to the true total variation. So therefore, for learning, it means we can learn arbitrary weights for these operators f epsilon. We just need to make sure during learning that they sum up to 1. That's it basically. And this is what we did. And we set up a bi-level optimization problem here with a loss function because just a quadratic function. The ground truth discontinuities I'm showing up the next slides. The inputs were the images with the gray shaded areas. And the lower level problem in the bi-level optimization is this total variation plus in-painting data fidelity term, which here is written as a saddle point formulation. And additionally, we had these constraints that the coefficients need to sum up to 1 for both components of the filters that interpolate the two components of the dual variables. And this is basically the reason why we wanted to solve this bi-level optimization problem, that we have developed this piggyback primary dual algorithm. So now this is the training data, this is the input, this is the desired output. And then we just used 64 different images because we only learned a handful of parameters for the discretization. We found out that just this small number of images is enough. And this is basically the filters, the interpolation filters we have learned. And we also applied some sort of symmetries. This actually nicely relates to the previous talk. So if we just have two filters, then of course, with a group of two elements, we can only ask for a transpose symmetry. So we at least tried that the learned total variation is the same if we transpose the image. And for more components, 4, we were able to require a rotational invariant by 90 degrees. And this, as you can see, this is not a continuous equivariance. We just asked for a discrete sort of. But for all these different discretizations we have learned, actually we have seen that it performs much better compared to the state-of-the-art discretization. So here the best handcrafted discretization is the one of Laurent Condard, written here as CD, Condard. And this can also be interpreted in our framework in choosing these interpolation filters as piecewise linear interpolation filters. Okay, so now with these learned filters and now evaluating this on our test data, we see that we can recover straight discontinuities almost perfectly for all different orientations. Of course, for some orientation, it's still a little bit better, but at least we didn't see any kind of blurring. And for the human eye, it is impossible to see if there is a blurring going on. Of course, there's some natural blurring coming from the grid itself, so this cannot be learned away because this corresponds to a partial pixel effect. So there's just a recent extension I would like to mention. We also did this in 3D. We learned on the catenoid, which is a minimal surface in 3D, and which gave us these filters here, where we also applied a transpose symmetry. And after learning, we can also, for example, compute famous minimal surfaces like the Schwarz P surface with very high quality. Because for the Schwarz P surface, there is no analytical solution available, so we cannot use these sort of surfaces for learning, but for the catenoid, there's an analytical solution. A very recent extension is that we try to learn shearlets. So shearlets is a very popular class of transforms in order to regularize images, and they are known to be optimal to approximate piecewise smooth cartoonish images. And they're usually just made of two things. There's one generator function as in wavelets and one directional filter. And from these two guys, together with the number of shearings and scales, you can generate the whole family of shearlets. And basically, we used again the piggyback primary dual algorithm to learn optimal generators and directional filters, as well as the lambda penalization parameters when we use this as a regularizer here above. And you see that both the generator and the directional filter significantly changed. In particular, this directional filter significantly changed. And if we compare a standard shearlet that we took from the toolbox and compared it with the reconstructed learned shearlets, you see quite a big difference. And this gives you improved denoising performance, for example, by more than 10%. Okay, now let me move to deeper regularizers. So together with Erich Kobler and Alexander Effland and Karl Kunisch, we have developed the so-called total deep variation. This is again a regularizer where basically first linear operator K is applied, and then the L1 norm or your penalizer is replaced by a larger neural network, basically that has some particular architecture. And of course, the task is now to learn much more parameters from data such that we get best performance for certain image reconstruction tasks. But basically, this total deep variation gives you a pixel-wise energy, and then the entire energy of the energy is basically obtained by summing up all these pixel-wise contributions. And you see here on more textured areas, the energy is higher, and for smooth areas, the energy is lower. So when we apply this to image denoising, we see that we get typical results like this, and comparing this with the previous result of the total variation, there's a huge difference in performance. Learning was done via unrolling in this work, and we used typically 5 to 10 iterations. But again, I would like to stress that the parameters are kept constant. So we really learn an energy. we compared it to the state of the art of this time, 1.5 years ago approximately, and it turned out that it compares favorably with the state of the art, but requiring only 1% of the parameters compared to more black box deep learning algorithms. Then, after it has been learned, learning took place on Gaussian image denoising. Actually, we can apply to different image reconstruction tasks like CT reconstruction. Now, of course, we did not make use of unrolling. We just took the regularizer learned on unrolling to solve this inverse problem here. And the same can also be done for magnetic resonance imaging. And it gave us quite nice results. Of course, compared to an end-to-end trained dedicated regularizer for the particular MRI or CT reconstruction, it has a little bit worse performance, but still we were quite happy with the performance overall, given that it has never been trained on CT or MRI images. So also quite recently, together with Thomas Pinetz, Erich, and Alexander, we also looked at the data fidelity term, and we also proposed to learn the data fidelity term in situations, for example, where we don't know what is the analytical expression of the noise. So if we don't know exactly if it is Gaussian noise or mixture between Poisson noise, Gaussian noise, and so on. And our general model for the data fidelity term is that it is pixel-wise. At least in some parts of the work, we assumed it is pixel-wise. So it boils down to learn the parametric form of this pixel 1D function, pixel-wise function d theta, parameterized with this vector theta here. And in some algorithms, we made use of the proximal map in a proximal gradient method. And therefore, we directly learned a parametric form of the proximal map instead of a parametric form of the data fidelity term. And if we ensure that the learned proximal map is one Lipschitz and monotone, then we know we have learned a proximal map of a convex function d theta, and we can then reconstruct from the learned proximal map the convex function d theta. We consider different structures on the data fidelity term, for example, that it is a Fréchet metric, or more general, we also consider the generalized divergence. So this is salt and pepper noise, but the algorithm did not know that it is salt and pepper noise. And now we are comparing what happens if we use a fixed quadratic data fidelity term and just learn to regularizer, or we used the fact that it is a Fréchet metric, learned both the regularizer and the Fréchet metric, and most generally, we learned both the regularizer and the generalized divergence. So in case we use the L2 data fidelity term, which is of course completely wrong in case of salt and pepper noise, then we get results like this typically. And it was quite astonishing to see that the regularizer can compensate for this completely wrong data fidelity term, but still the results are not very good, I would say. Then we allowed the data fidelity term to be a Fréchet metric, for example, a difference of input and output, a function of the difference of input and output, which gave much better results, as you can see. And finally, we also consider the generalized divergence, and this gave clearly the best results. Most freedom usually give you the best results. And compared to the ground truth solution, of course, we miss a little bit, but you see the results are quite good. So now we can visualize the proximal map and the corresponding convex data fidelity term that has been learned. In case we said, okay, let's learn a Fréchet metric. This is how the proximal map, so this is the input and the output of the proximal map looks like. Now we can compute from the proximal map this convex function d theta, and this is how the convex function d theta looks like. Fréchet metric basically means that these guys are all parallel, and when we would cut here diagonally through this function here, then what would we get? Exactly an L1 norm. So in case we say learn the best Fréchet metric for salt and pepper denoising, it learned exactly L1 data fidelity term, and the proximal map is therefore just soft fringe. In case of generalized divergence, this is how the proximal map looks like, and this is how the corresponding convex function looks like. And here the algorithm, at least I think, was very clever, because it learned from the data that salt and pepper noise has just black and white pixels, and it should just in-paint the black and white pixels and keep all other images. And this is basically seen in this function here. So it learned the 0,1 in-painting mask. So to keep all images which are not black or white and just in-paint the black or white pixels. And this has been learned from data. So what about unsupervised learning? So I've mentioned the connection between energy-based models and Bayes' theorem, but now what happens if we completely ignore the data fidelity term and just would like to learn a regularizer from data? And the big advantage here is that we don't need exact pairings between input and output. We just would need to have access to a database of nice images. For example, nice medical images, nice CT images, nice MRI images, and so on. And I've already explained to you that you can do that via standard maximum likelihood learning, and which means that on the set of given images dx, we try to find parameters such that our regularizer has a small energy. And here on the right-hand side, this is this intractable term, which basically comes from the partition function. And this involves the integral over all possible images x. And on this soft min of all different images x, the energy should be increased. And of course, this term is untractable, so there's no chance to approximate this term in the general setting we're considering. But there are quite efficient sampling algorithms, such as the unadjusted Langevin algorithm, and we basically make use of this algorithm, which also needs to have access to this energy here in order to approximate this term. And in this setup, we used a quite agnostic regularizer, which is just a neural network that takes as the input the image, has different layers with convolutions and just leaky relo activation functions. And in the end, it outputs just a scalar, which is the energy. So the neural network doesn't compute the solution here. The neural network computes the energy. And here in this example, it has 12 million parameters roughly. And basically, we learned the regularizer on a set of CT images. Just on the CT images, no sinograms available, just the CT images. And after learning, actually, we can start to sample images from the learned energy. This looks similar to generative adversarial networks, but really we learned that energy and then used Langevin algorithm to sample from the energy. So there was not this generate and discriminator. We just had one thing that was the energy. And you see that the samples look quite natural. Sometimes there's a hole in the body, but who cares? But it at least shows that we have learned something reasonable from data. And after learning, we can then make use of this regularizer to solve different inverse problems. So here I just mentioned the limited angle tomography and compare it to some state-of-the-art algorithms. So this would be the reference reconstruction, but now in our inverse problem, part of the sinogram is missing, so that, for example, with standard filtered back projection, we cannot reconstruct this part of the image. Even with the SART algorithm, which basically just minimizes the least squares term, we see that this part cannot be reconstructed. Well, we only see a small hint that there might be some information available in the data that gives a hint where the correct edge should be. Also with the total duration, we are out of reach, so it gives a discontinuity here for the body, but comparing to the ground, it's obviously wrong. And with this quite strong regularizer, we have learned, unsupervised, we have access to the images, but nothing more. Actually, we get quite nice reconstruction, and this outperforms the other methods by quite a large margin. Now we can check what did we reconstruct. As I said, the SART gives us some hint where the true discontinuity of the body here is. And now comparing this with the learned regularizer, we see that it indeed gives us a reconstruction that makes use of this little information. It gives you just the most likely reconstruction given the limited amount of data available. So what we can also do, of course, our learned prior together with the data fidelity term defines a posterior, and we can also sample from the posterior, and then we can make an uncertainty quantification of our reconstruction. On the left-hand side in this video, you see samples from the posterior, again computed with Langemin. Then here we see the expected reconstruction, which is basically obtained by averaging these guys here. And on the right-hand side, we also computed the variance. And this nicely shows that in parts where there's not so much data, there's more variance. And this nicely corresponds to the fact that actually we have limited angle tomography, where the reconstruction should have more variance here. And this is nicely reflected here in the variance computed from the posterior. So I'm ready to conclude. I was talking about energy-based models, and I think they provide a very flexible class to solve a number of problems in vision, also in machine learning. And I think there's a lot of more to come and a lot of open problems we need to work on. I talked about different examples where you can make use of learning to improve energy-based models. I talked about learning better discretizations to get more rotationally invariant discretizations of the total variation. I talked about the shear-led transform, that you can get a better shear-led transform that fulfills all the properties necessary or of the shear-led. And last but not least, I was talking about full energies that are represented by neural networks. So they lead to state-of-the-art results on a variety of problems. You can learn them with different algorithms with maximum likelihood, bi-level unrolling, and so on. Thank you very much for your attention, and I'm happy to take your questions.
That's a super interesting talk. We have time for one or two quick questions before going to lunch. Yes, Matthias?
Very nice talk, Tom. I've got maybe kind of two, like one clarifying question and then two content-wise questions.
Yeah.
Like this R that you learned in the end, was it convex or non-convex? Like
Sorry?
E example.
The last example? This one?
Convex or non-convex regularizer?
This was non-convex, of course. So I think you could try to make this convex. We have this on our agenda, but I'm afraid then the performance goes down because you really need these different modes.
And so kind of like when you sample, then sort of like it's just like images which are fairly small energy, probably not minimal energy, I suppose.
Of course, you don't, when you sample, you don't have a guarantee that they have the minimal energy, but as is showed here in this video, I mean, we just initialized it from plain noise. So they converge to different modes, and all these modes represent different images. This is my comment in the beginning that sometimes it might be desirable to have non-convex energies, because this allows you to represent really different flavors of images. And I think this is necessary at some point.
And then the variance image you showed. So how does this compare with the variance image for TV, for instance?
Good questions. We haven't compared that, but yes, I don't know. Of course, you can do the same with TV. You can do the same with TV. Just take the TV posterior and make Langemin on that, and it would give you also something. Yes.
So the question is, like, does the high variance, let's say like in top left and bottom right corner, does it come from that because you try to really infer information where, like, in the data there's very little information?
Yes, exactly. This is the more or less the kernel of your operator. It gives you much more freedom here, and therefore, you know, the likelihood plays together with the prior, so the prior has more freedom in this area, and therefore you get more variance in these areas. Yes.
Tiny one more.
Yes.
Like another one. So like if you now learn on CT images and then so like you now apply this to, I don't know, like in-paint pics.
Yes.
Would you then see CT images where you, sort of like?
We did the other way around. I didn't show you results here. So what we did is we learned on CT images, and then we made artificial images pasting, for example, the cameraman to the liver or to the heart. And what we see is it can reconstruct still the cameraman part of the liver. But when we sample from the posterior, we see also a higher variance there. So it's not very happy, the prior with the cameraman, but it still can reconstruct the cameraman there.
I think we have a couple of questions in the chat. One is about the shear-led learning example.
Yeah.
One, it says the learned univariate mother function does not seem to have vanishing moments. Why is that?
Can you repeat it, please?
Yes, the learned univariate mother function does not seem to have vanishing moments.
You mean in this learned function H, the generator function H, or the learned P? I have to admit I'm not an expert in shear so maybe this can be clarified a bit more. So what we did is we learned this function H, then this W is computed from H and the wavelet corresponding to H, and this J is just a scale, and we did exactly the same construction as in the shearlet. We also had constraints that the norm of H is somehow limited, and for this directional filter also the norm was, I think L1 norm was 1, so that the Lipschitz parameter of the corresponding convolution operator is 1. So we tried to keep the constraints, and we were not able to find out more constraints, but maybe this person in the chat, I would be happy if this person writes me a mail and saying maybe there are additional constraints we should take into account, but we couldn't figure out which more constraints we need to apply there in order to make this a valid shearlet. So we thought this would be enough, but it's easy to get more constraints in the optimization.
Yeah, and the person thanks for the feedback.
Okay.
And the last question is about slides. If you will make available the slides somewhere.
Can you repeat it? Sorry, it was.
Like if the slides of this talk will be available somewhere.
Yes, I think I've uploaded it already.
Okay, great, thank you. And yeah, I think Simon has an announcement before we go
just
to
a
lunch
quick,
break.
sorry, everybody, yeah, just to remind you, we have the discussion session, 3:30. So we'll do this sort of on the whiteboard, but we will have the people online. We'll use a whiteboard in Zoom. So reminder just to send in any suggestions of topics that you want to talk. We've got a few, but it'd be nice to have a few, just the general high-level topics we want to discuss, and we'll see how it goes. It's done this before in hybrid meetings. It works quite nicely. So let's try and have an interesting discussion. 3:30, so in here, and online in the normal channel.
Okay, thank you, Simon, and we thank Thomas and all the speakers from this morning again.